Okay. How are you, everyone? We continue with the method of counting. So this is something that someone actually asked last time on multisets. So sets where you can repeat elements. Okay. So this is a snapshot of where we are. So different methods of counting, including selection of items from sets where you either select them in a sequence, as you think of your selection as a sequence, in other words, it's ordered, and you allow repetitions. So this is just corresponds to picking a fixed length string over some alphabet. Or if you're choosing an ordered sequence, but no repetitions are allowed, you are, with every choice, you are reducing the alphabets from which you are choosing. But that's okay. This is the formula, and it's called a permutation. Here it should be T permutation, not N permutation, because T is the length. Now, if you are picking unordered, so it's not a sequence, it's a set that you're choosing, and there's no repetitions, then, well, it's like this, the way of counting is like these objects, but you eliminate the internal orders, meaning that you divide this by T factorial. And there's a special symbol for that. It's the whatever cardinality of set A, choose T. In addition, we also show something in between these, which was ordered sequences, but with fixed number of repeats. So repeats were allowed, but they were fixed. So it was like this permutation of the Mississippi letters, right? You had 4 letters of S, a fixed budget of repetitions for each kind. And we had a formula for this. I should have brought this here, but it was A factorial divided by these internal budgets, factorials of these budgets, because the repetition of a given letter means that the internal permutations of occurrence of these letters are disregarded, just like here we divide by T factorial, meaning we disregard the internal ordering of all these chosen T elements. But here is a natural sort of things that completes this puzzle. What if you have repeats allowed and unordered object? So the set you choose, the internal order doesn't matter, but you can allow for repetitions. So what is this even? Because it's like a set, there is no ordering, so it's a set, but repetitions are allowed. As far as sets are concerned, that makes no sense. We said, no, there is no point like taking the same element over and over into the same set. The set doesn't grow if you do that. So this is something we call multiset. It's unordered, so you can just as well represent it in the canonical order from, if you have some, you have some lexicographic order on these objects, right? In this case, these objects are integer numbers, so there's a natural ordering between them. Let's just represent them from the smallest to the largest, and denote how many times a given element repeats. So these two things are, yeah, it's the same multiset, because I just changed the ordering, right? I just switched 5, 7, and 7, 5. So because the ordering of these does not matter, but what matters is the multiplicity of occurrences. So for example, here I have just 2 occurrences of 2, and here I have 3. So as a set, this would be the same, but as a multiset, it is not. Okay, and that's, it's not the same as a sequence where no, these are the same as multisets because they have the same elements with the same multiplicities, but they're different as sequences. So what kind of problems come up as like that counting multisets is a natural representation for such problems? Well, okay, so you're going to the donut store and getting 12 donuts, and there is 4 flavors: chocolate, glaze, jelly, maple, and you all chocolate donuts are the same, and so your selection is a decision of you have a budget of 12. How many repeats of chocolate do you want? How many repeats of glaze? How many repeats of jelly? And then when these are fixed, the maple is already determined because it's 12 minus whatever multiplicity of these you chose. Okay. So how many ways are there to select? Okay, in this way. It is not exactly like our Mississippi example. In fact, it's not at all. In Mississippi, you had fixed budgets for every letter type. If you think of letters as denoting donuts, then it's as if you had a fixed budget for every donut. And in particular, the sum is also fixed, right? But in Mississippi case, the ordering mattered. Here, the ordering does not matter. It doesn't matter whether you choose your 6 chocolate donuts first and 2 of each glazed jelly maple second, or first choose glazed jelly maple and then 6 chocolate. These are the identical choices. So it's sort of the exact flip. It's the multiplicities matter, not the order. In the Mississippi case, multiplicities were fixed. The internal ordering is what mattered. So here is the sample selection, right? 3 chocolate, 1 glaze, 6 jelly, and 2 maple, right? How do I count these? Well, let's have a canonical order. So the types, let's call them, not coincidentally, I wrote them in alphabetic order, okay? So now, once you put them in a canonical order, then you can see, okay, well, what am I choosing here? I'm choosing boundaries because it has to start with the chocolate and end with maple. And the only thing I'm choosing really is I'm shifting boundaries. Maybe I don't want the chocolate at all. So therefore, this chocolate glazed boundary is effectively right here. And right, so I have 3 boundaries because I have chocolate glaze boundary, glazed jelly boundary, and jelly maple boundary. If I put chocolate glazed boundary right here and jelly maple right here, I don't have any chocolate and any maple. The only thing I have some bunch of glaze and then some bunch of jelly. Now, these 3 boundaries are ordered, right? But you can just represent them as bits, right? Because the first boundary will always be a boundary between chocolate and glaze. The second boundary will always be interpreted as a boundary between glaze and jelly. So you can just as well denote them as just as bits, right? Because they only tell you, okay, you always say, okay, I start with chocolate. When I encounter a boundary, I switch to the next flavor. I increment my flavor type count, and I go from chocolate to jelly to glaze. So all you need is bits that tell you where the boundary is. So we are almost at the representation, because you can represent them as a binary code word where ones designate switches between the types. In other words, there's a bijection between donut selections and these binary code words with exactly 3 boundaries, the 3 ones, okay? So here is how the encoding works. I split them like this, and I put ones at the boundaries and zeros everywhere else. So in other words, so the encoding is that if I tell my body, okay, here is the encoding of the donut I want you to buy, then then he will interpret this encoding like this. At the beginning, he's fixated on chocolate, and every time he gets a 0, he puts one donut of the current flavor. When he encounters a 1, he switches the flavor to the higher one, and recursive, right? If he sees a 0, then he picks a donut, but now from this current flavor. If he has a bunch of 1s in a row, that's okay. He just increments the flavor type, and then once the 0s start, he starts buying of whatever the current flavor is, right? So every code word that it describes a selection of some 12 out of these 4 flavors have to have 12 zeros, because the zeros mean pick a donut. So the total budget for zeros is 12. And 3 1s, because you switch flavors 1, 2, 3 times. Now you can say, well, what if I want all chocolate? I don't switch any flavors. No, you do. Just put all the 1s at the end of the string. There are useless switches, right? Like you just have 12 zeros, buy all chocolate, and then 3 1s for just switching context. It's still a valid encoding, right? And it's a unique encoding of that particular selection. So just get us 12 chocolate donuts as a 15-bit binary string with 12 zeros and 3 1s. This is indeed a bijection. So, okay, like I'll convince you that it's a bijection by just running for examples. So I would encode 3 chocolate and the rest jelly like this. 3 zeros at first, context switch from C to G and G to J, then a bunch of zeros for all the J's, and at the end, this useless quote-unquote context switch to the last flavor, but no zeros afterwards, right? Because we exhausted the budget of zeros. All glazed would look like this: context switch, 12 zeros, switch, right? So every word will have exactly 12 zeros and 3 1s. Every binary word that satisfies these constraints corresponds to a donut selection because it has 12 zeros and because it has 3 1s. So therefore, you can encode only 4 flavors, right? Every binary word is a bijection because every selection has a unique binary word, right? Using this procedure. Okay. So now, okay. Okay, so let's check that we know how to parse this, right? So what selection is this? Chocolate, switch, 3 G's, switch, 1 J, and the rest of M's, right? I mean, okay. Here I context switch. So these are all the J's, right? Okay. So now, if I convince you that this is a bijection between these 12 so how long are these strings? They are the number of donuts plus the number of flavors minus 1. Okay, these are how long these strings are, and the number of 1s is number of flavors minus 1. Okay, so now how many bit strings are there like this? They have a fixed fixed length, 15, and the only thing you choose in them is that you have a fixed budget of flavor switches, which is 3 for the number of flavors minus 1. But that's we know already, right? You have 15 positions and you choose 3 of them to place 1s into. The 3 1s you're choosing position for them. So it's 15, choose 3, right? So this is the general solution. You have n items. They come with m varieties, m flavors. You can encode them. There is a bijection between such selections and binary strings of length number of items plus the number of varieties minus 1, because that's the length of each encoding. And now what the encoding is about, the number of varieties minus 1 is the number of these boundaries, the variety boundaries that you're going to place. So so this is the length, and this is the choice of the number of positions that you have to choose, right? And this formula, in my example, n was largish, right? 12, and m, the number of varieties, was 4, was smaller. But actually, they could be the same, right? This still makes sense. Let's say that the flavor, there was 12. There's 12 type of donuts, and I want to buy 12 donuts. No contradiction, right? In fact, the formula then will be 12 plus 12 minus 1, 23, choose 11, right? Because the whole string has to be the number of donuts I want, 12, plus the number of flavors minus 1, 12 plus 11. And so if I switch, so I buy 4 donuts, but there's 12 flavors in the store, that's okay. So my strings have length 15, and they have, if there's 12 flavors, so they will have 11 ones and only 4 zeros, right? Because I buy 4 donuts now, so I only have 4 zeros, and I will have 11 context switches, right? So that, because I have 12 flavors. So it's okay. It doesn't, these numbers can be in any relation like this, right? For previous type of cases, this wouldn't make sense, right? Like you cannot pick a sequence of n from m characters if with well, but yeah, if the, well, okay, yeah, okay, I can pick if I am allowed repetitions, then of course I can pick from a smaller alphabet a large string. Okay, so okay, well, this is the same kind of examples. There's 75 varieties, and I select 12 candies from them, right? So this would be 12 plus 75 minus 1 over 75 minus 1, right? So a string with 12 plus 75 minus 1, so 86, with either 12 zeros or 74 ones, right? Like however way you want to count, you want to look at it. So this is the way we looked as so far. But notice that these two quantities are the same, right? Because m minus 1 and n sum to n plus n minus 1. So, okay, let's say there are 4 computer types, and you have a computer cluster with 25 computers. So, how many clusters can you have, right? So it's like you take 25 donuts, and there's 4 varieties of donuts, right? So it's 25 plus 3 over 3. I mean, choose 3, right? Because there's going to be 3 context switches, because there are 4 donut types. Okay, let's try to wrap all these counting problems into a sort of a uniform framework. This framework is called balls into bins, okay? And it is a very useful way to conceptualize like problems of selection. And in particular, in computer science, it's very often the case, like you hash the, data into a table, you literally have objects falling into bins, which are outputs of the hash function. And you're concerned typically with things like, what's the chance that a lot of items are going to be placed into the same bin, and I will have an overflow in the data structure. So imagine that you have m bins, and you're throwing n balls into the bins. Now, let's the bins will always be distinguishable, so we'll treat them as separate bins from 1 to m. And so, for example, if all balls fall into the first bin or all balls fall into the second, that's a different assignment. Balls, on the other hand, we can conceptualize them as all identical. Okay. So the only thing that matters is the multiplicity of balls that fall into a bin, or they're different, they're labeled. So it's not just multiplicity, but like which ball, right? So it's like if balls have numbers. And now, so these are the basic two different varieties of these problems. But also, you can have a natural constraint that once a ball fell into a bin, then no other can. And that constraint can pertain to both the problem version with identical, where all the balls were the same, or where balls are labeled. And likewise, if there is no such restriction, right? So balls can be placed anyway, like in this hashing application example I started with. And that will be a different version of the counting problem, right? So if you have n balls that fall into m bins, this is the way to count them. Why is that? Because these n, if you have a constraint, sorry, that there is only one ball per bin, because balls are identical. So what the ball does by falling into a bin is you're just selecting the bin. You're turning the bin on. And if there is no ball, then the bin is off. So you have n balls. So basically, you're selecting n bins out of m. And of course, m choose n is the number of such selections. It's the way, how many ways are there to choose a subset of n bins from a set of m. Now, if the balls are, I still have this constraint, and the balls are all labeled. So I'm not only choosing the bin, but also I'm labeling the bin by the ball. Think of the balls as just labeled from 1 to n. And think of the number that falls into a given bin as, okay, I'm going to, when my balls fall into bins, and I chose the n bins out of m, and now I will naturally order those selected bins. The one where the ball number 1 falls is the first one. The one where the ball number 2 falls is the second, and so forth, right? So what did I do? I chose n out of m bins, and I ordered them. So it's a permutation. Out of a set of m, I choose n in an ordered way. And where did the order came from? Because of the labels in the balls. The balls all had different labels, right? So there was like let's order them from first to end. And that means that I'm choosing bins in an ordered way. The first ball chooses, the ball labeled 1 chooses the first bin. The ball labeled 2 chooses the second bin, right? And here, because all the balls were identical, there was no such notion. I didn't have first bin or second bin or third bin. I just had set of bins that I chose. Okay, now what if I remove the constraint? So balls fall, and now if a bin is taken, it still can be taken again by another ball. Let's start with a different one, right? So you have these balls which fall into bins, and every ball has m choices, and they're all independent, and each of the n balls make that selection. M selection for the first, M selection for the second, etc. Right? So it's M to the N, right? Again, this is as if I have an alphabet of the size of the number of bins, and I created strings from it, right? The first character is what the first ball fell on, the second character is the second ball fell on, etc. Now, what if I change it to identical balls, right? So I'm choosing M. Well, no, I don't. I have M bins and N balls, and now the balls can come in some multiplicity into a bin. Does this remind you of something? Right? What you're doing, you have these indistinguished balls, right? Like they're all the same. They have no labels, no, right? And the selection was how many, you had a fixed budget of balls, N. And all your choices is like, how many of them are you placing in the first bin, how many in the second, how many in the third, etc. Some of these bins can be empty. Perhaps all the balls came into the first bin. Perhaps they were, evenly spread if the number of balls and number of bins is the same. What does this sound like? So, okay. All right, maybe since the problem of recording is that, if I wait, then the people who try to watch it will not appreciate it. So, okay, it is like this choice of donuts, right? Because the bin is a donut type, and you have a fixed number of donuts you're purchasing. It's the number of balls. Indeed, if bins were flavors, you could represent your selection of 12 donuts as this balls into bin problem. You have 12 balls, and you're throwing them into 4 bins. The bins designate flavors, they're ordered. The balls are all indistinguishable because it's the only thing that matters is how many are in the chocolate flavor, how many in the glaze, how many jelly, how many maple, right? So that's the same. That's the instance of the problem we have just seen, right? So this is a very natural interpretation of each of these problems we have seen, of the counting problems we have seen. I guess the Mississippi thing, the permutations with repetitions are not here yet, but they also have a natural interpretation in this framework. So, okay. So in other words, if we represent the solution, if we try to map it like in our set of traditional representation, not balls into bins, but as strings over an alphabet. So the alphabet is the bins, and let's see what how does this. The selection of these m bins, it means that I'm taking a string of size n that has no repeats, and it's not a string really, it's a set. It's unordered because the balls have no labels. Okay. Now the balls have labels, so it's a string, not a set. I'm choosing the bins in an ordered fashion. It makes the difference whether some bin is chosen as the first one because ball number 1 went into it, or the second one because ball number 2 went into it, right? So this is the number of strings that you can make out of an alphabet of size m. Of the strings are of length n, and you don't have repetitions. Now, what about this? Okay, this is ordered with repetitions, right? This is the basic alphabet problem, alphabet of size m, and you have n characters. And what? How do I interpret this as a string? So it is not a string; it is a set, and it's a multiset, right? Repeats are allowed, right? Because I'm taking these balls. Hold on a second. So actually, let me ask you. So I have a piano player in the other room. Did you hear that very badly? I don't know how it looks on the deck. So maybe I ask that. So, Kotku, ja mam lekcję teraz, także wiesz, musisz chyba, nie wiem, umów kino. Okay. Sorry about that. Dobra. Okay. So, okay. Well, I guess opinions differ how bad the background is. Well, thanks. It's okay. Okay. So here we were selecting n objects out of them, and repeats were allowed, right? Okay. So this is just goes over the example I was talking about. That if balls are identical and bins, I can think of them as my flavors. That's what I was talking about here, and that's why this is the formula. Okay, so I'm just repeating myself here. So here is another multiset example. Let's say there are prices, but they're identical. So the only thing is like a multiplicity, okay? And you give it, there's 200 students. So you're throwing 10 balls into a group of 200. And the bins, it's okay if many balls fall into the same bin. In other words, you're choosing 10 donuts out of 200 flavors, right? With repeats allowed. So, it's now if we can so let's cut to the chase. So this is right. So this is the selection of n candies from 200 flavors. And now if a natural constraint in this case would be that okay, if the prices are identical, then it makes no sense to choose to give 6 of these identical prizes to the same student, right? So if you have a limit, then now these identical balls can fall into bins, but now once a bin is chosen, then no more ball can fall into it, right? So you have to just choose 10 out of 200 bins. This, by the way, is a smaller number, right? Because if you are allowed repetitions, then the number of selections will increase. And if you have 10 different prices for 200 students, right, then it's like this, except it's ordered. So it's 200 factorial over, this whole thing divided, multiplied by 10 factorial, right, which is this. And finally, if you have different prices and there is no limit on the number, then it's like choosing, these 10 balls can fall completely independently. So it's 200 to the 10th, the number of choices. Okay, some variants of these. So for example, okay, so we are distinct. The bins are always distinct, and the balls are now identical. So here is another class of applications where you can use this these balls into bin reasoning. You have an integer equation where you say, okay, the variables have to be positive, or here non-negative, and they have to be integers. Okay, so how many solutions are there to this equation? Well, that's exactly the number of selections of 12 donuts out of 4 flavors, because making this whatever unit is like, that's how many donuts of flavor 1 I'm choosing, and the total multiplicity of these must be 12. So I have 12 units that I have to distribute between these 4 variables, and the minimum value is 0, right, because they are non-negative. So this is exactly the problem of choosing 12 donuts with 4 varieties, right? So each of these solutions will can be encoded, like how many units I put into x1, how many units into x2, etc., right? So for example, this one is encoded like this. So it's 15 choose 3, number of units plus number of flavors minus 1, choose number of flavors minus 1. Okay, so very natural type of question, and it's the same problem in the end, right? It's the same combinatorial problem. So now let's introduce some variants, because here I had a okay, I had a variant. I said that okay, I want these numbers to be non-negative. What if I complicate this, saying, okay, I want like this, that like one variant, let's say chocolate, must have at least 2. Okay. Well, so that variant is like really not any harder, because if somebody tells you that, okay, you can consider all choices except that chocolate must be at least 2. Okay, so that means that out of the 12 donuts, 2 will be set aside as chocolate ones. The remaining 10 can be chosen arbitrarily, right? So it just reduces the problem of the original problem, except with reduced number of donuts, right? So this becomes the problem of choosing 10 elements out of the 4 types instead of choosing 12, because 2 of them, the choice was already made for you. Right? So it's the same problem type, right? You just if you have this type of constraints, at least 2 of one type, at least 1 of another type. This means that these some number of donuts have to be placed deterministically into these flavors, so they're sort of gone from the budget that you have a choice about, and the remaining ones is just the original problem, but with the smaller donut count. So okay, so here is a variant of this problem. I'm looking for integer solutions, a number of integer solutions which are non-negative, and I have some constraint that x2 must be at least 1 and x4 must be at least 3. Okay, so I have 12 units that I have to place in here, but 1 unit I have to place in x2. I don't have choice. After I do that, then the constraint is satisfied, but any additional units are fine, including no additional units, right? 0. 3 units have to be placed here. So 1 plus 3, I take 4 units deterministically into 1 here, 3 here. I have how many remaining? 8. And I can freely choose them anywhere here, right? So it's really a choice of 8 balls into 4 bends. So it just reduces to the original formula, but with a reduced number of the reduced budget. All right, 4 were gone to satisfy these constraints. So it's the same thing, like as far as like throwing balls into bins. Let's say that I'm throwing 12 balls into 4 bins, but at least 2 must be in each bin. Okay, so I'm wasting 8 balls, right, to satisfy this constraint, 2 in each bin. The remaining 4 are free to be chosen anywhere, right? So it's 4 plus 4 minus 1, choose 4 minus 1, right? Because it's the original problem, but with the dramatically reduced n, right? Instead of the original 12, I have just 4 balls that I place in here freely. Okay, and in which case this would be the formula I will use. Okay, so say I have 15 chocolates and 5 kids, right? So 15 balls and 5 kids, and each kid has to get at least 1, but the chocolates are identical, so the multiplicity is the only thing that matters, right? So I take away 5 pieces to satisfy the constraint, place them one in for every kid. The remaining 10 are free. Okay, so it's the formula applied to 10 balls, right? I'm basically placing 10 balls into the 5 bins with no constraint. In other words, I'm choosing 5 flavored. I'm choosing 10 of 5 different flavors of 10 objects of a multi. I'm choosing a multi-set of size 10 whose elements are 1, 2, 3, 4, 5. Now, let's say I added an upper bound. So I want you to get me 12 donuts from 4 varieties, but no more than 5, let's say, of chocolate. Okay, so instead of giving you a lower bound, which was easy to satisfy, you just used whatever number of balls to satisfy this lower bound, and then it was a free choice. But what about the upper bound? There is more variability, right? Okay, they're very easy to count using the what we call the complement principle, or complement rule. So it's just counting by complement. So the number of choices which satisfy this constraint, the upper limit constraint, is the total number of choices minus those that don't. What are those that don't? It is those that don't satisfy this constraint are those that violate the constraint, right? And how do you violate this constraint? You have at least 6 chocolate. That's who violates constraint, 6 or more. And that we know how to count, because that's a lower bound. If you look at what are these violation selections, they are selections that satisfy this lower bound. So we know how to count them, right? 12 out of 12, 6 I wasted to satisfy this constraint, 6 remaining into 4 varieties, right? You know how to do that, right? So it's this formula, 6 plus 4 minus 1, choose 4 minus 1. This is this guy. And in here, well, we have the original formula applying to 12 donuts, right? So it's this. You can try to count this differently, right? But it will be more complex. And this is a simple way. Okay, now, so let's say there are 75 candy types, and you select 12, but this the constraint is that that she cannot buy more than 7 pieces of strawberry, okay, of some flavor, because there's only 7 pieces left. Okay, so that's exactly this constraint we had before. You have to do less than 7 of certain flavor. So let's count always and subtract those that violate it. In other words, subtract those where the number of the strawberry flavored is at least 8. And you know how to do that, right? Because so you waste now 8 out of 12 to satisfy this constraint. And so you effectively have 4 candies left to distribute among 75 types, and that counts this stuff, whereas this is the original formula, right? You have 12 and you're choosing 75 types. Okay, so the same application. So let's try a summary look once more, and expand the table of possibilities a little bit. So we have M bins, which are going to be always distinguishable, labeled from 1 to 5, and N balls, and sometimes the N balls can be labeled. Each one is different, or they are all gray. Sometimes we'll have this at most 1 per bin constraint, and we'll have no constraint. Or here is the natural constraint, same number in all bins. Okay, it's like it's between these two. Okay, so we already know how to fill these up, right? Because we just did so. If the balls are indistinguishable, so we're here, and there's a limit, okay, then it's like we're choosing 3 bins out of 5. Yes, so this is the I should have this color stuff here. We're choosing n bins out of M. Okay, so it's M, choose N. Now let's move here. The balls are all labeled. Okay, so we are choosing the N out of M bins and in an ordered fashion, because these labels can be like 1, 2, 3. Okay, so it's the ordered selection, which we already had before. Now let's say that the balls are different, and there's no limits. Oh, I should make them different color still, sorry. So that's each ball is independent, right? The first ball has 5 choices, the second 5 choices, the third 5 choices. It's this. It's the number of length from the bin alphabet of size n, right? The string that represent my choices of length n. Now, if I allow the repetitions, but the balls are all gray. Well, that's the taffy selection problem, right? The bins are my taffies, are the flavors, and the gray balls are like just the number of taffy budget I have, right? Of a donut budget. So it's the n plus m minus 1 over m minus 1, where m is the and notice, by the way, it doesn't matter whether you take n minus no. Oh, m minus 1 or n, but yeah, no, m minus 1. Okay. Sorry, what I was gonna say is that you can replace this with n, because you know, 5 choose 2 is the same as 5 choose 3, right? Okay. What about these? Because these will be new. So if every ball is different, is labeled, and you placing them into these m bins, and you have a constraint that every bin has to take equal number of balls. First of all, the number of balls must, the number of bins must divide the number of balls, right? Otherwise, you cannot satisfy this constraint. But let's say that is so. So, for example, you have 5 bins and 10 balls, and each of these has a different color. So, what is this? Well, so I can maybe look at this like this. Write out these balls and permute them, right, in any way you want. But not all the permutations would mean that you're having a different selection. So, for example, if I switch gray and black, I'm still having the same selection. Or if I switch light blue and yellow, so the internal permutations within the bin don't matter. So therefore, it's the total number of ball permutations n factorial divided by internal permutations of this, of how many are there. So the number of balls within each bin is n over m. So this will be n over m factorial number of permutations inside. Then I have to also ignore the same n over m factorial factor for internal permutations of these, and so forth m times. For every bin, I have to subtract, I mean, not subtract, but divide out these internal permutations. We have seen this formula, right? This is the Mississippi thing, because if so where is the, you know, if I represent them as the letters which I'm permuting, right? So hold on, where are the yeah, how do I see this as a, how do I map this into the so I have I have same I have a multiplicity of every letter. I guess my letters are the bins are my letters, right? That was so in the other examples. And I have a fixed multiplicity of every letter. It's 2 here. And these 2 balls tell me where should this bin 1 letter go. Which position in the string should bin 1 letter occupy? So balls, because they're different, you can think of them as positions in the string. The first ball is first position, the second ball second position. So if I order these balls from, you know, lightest to darkest, then let's say yellow and this gray are the, this is ball number 1, this is ball number 2. So the bin 5 letter will occur in the as the first character, bin 2 letter as a second character, and the black ball, the darkest ball, would mean that the bin 5 character is also at the end of that 6-character word, right? So you can also think of these as strings. So representing these assignments, you can represent them as strings of length, the number of balls, that are filled in with characters from an alphabet, which is the number of bins, and you have a strict budget for every letter, n divided by m, right? So yes, it is the permutations with repetitions, and so this is the formula, right? And now if I made all the balls gray, so they're now, so this was the distinguishable balls, right? If all the balls are gray and I have this constraint that I have to place 2 into every bin, then in fact there is no choice, right? There is no choice here. So the final elements of this table look like this. Okay. So let's do one more sort of counting type. It's the inclusion-exclusion principle. Okay. So when we started, we set the sum rule. We talked about the sum rule. Okay. It was one of the simplest, counting principles we did, which was if you're choosing from different sets and you have to choose from a union of them, but you know that these sets are disjoint. Like, for example, this is a set of all letters, capital letters. This is a set of lower cap letters. This is the set of digits. This is the set of letters from some other alphabet, Arabic, Hebrew, right? Korean, whatnot. And you have to choose a letter from one of them. Okay, well, it's a union and they're disjoint. And so because they're disjoint, so the number of elements here is just the sum of the cardinalities of each of these sets. But what if they were not disjoint? Okay, so that complicates it. How do you count basically cardinality of a union if the sets are not disjoint? Here is an example. How many strings of length 6 over alphabet ABC starts with either C or D? Okay, so I have 2 subsets. One is the set of strings of this alphabet that start with a C. The other set of strings of this alphabet that start with a D. Now these 2 sets are gracefully disjoint. You can either start with a C or start with a D. So that's great because it's easy to count strings of length 6 that start with a C. Basically the number is the strings of length 5, right? Because the first character is fixed. So it's 3 to the 5 is the number of 5-character strings of this alphabet. And the other set, the one that starts, whose strings have to start with the letter D, it's the same way of counting. Now, what if I change this and oh, okay, some 7 says it is not posted. Yeah, it's not posted yet. I will post after the class. So what if you change the constraint so that you want to count characters that start with a certain letter and end with the same one. So here is the thing. So the 6 characters that start with, sorry, if I had an and here, that would be a intersection of 2 sets that I actually know how to count. It's rather simple, right? If it was starting with a C and ending with a C, that's simple. The first and the last letter are fixed. I'm just choosing the 4 middle letters, so it's 3 to the 4th. But here I have an or. So I want this 6 character string to either start with C or end with C. I have 2 sets, and I'm choosing from their union. However, these 2 sets are no longer disjoint. You can have strings that start with a C and end with a C. But that's simple. You want to count cardinality of the set, count cardinality of both of them, and subtract the intersection, right? Because intuitively, when you sum up everybody in A1 and everybody in A2, you're double counting those who are in the intersection, so you have to kick them out. Okay, but just once, right? So now, yeah. These sets we already know how to count, and the inner thing I said we know too, right? Because it's like the previous problem, but even easier. The first and last letter are fixed. It's if the sets are one-to-one mapped to some predicate, you can say, okay, I want to count objects with some property, but the property is a union of property P1 and property P2, and so the union of these is cardinality is the number of sets with the property P1 plus the number of sets with property P2, and I have to remove one cardinality of the intersection because I double counted all the elements here. Okay, let's use it in one of the card playing examples. You have how many 5-card hands have exactly 1 king or exactly 1 ace, but also both possible, right? It's not an exclusive or. Okay, so let's count. Let A1 be cards with exactly 1 king. Let A2 be hands with exactly 1 ace. Okay, and now the intersection is non-empty because you can have 1 king and 1 ace in your hand. So the counting this union, the cardinality of this union, we can count them using this formula, right? So let's see how many cards satisfy this constraint, right? So you have 4 ways to choose a king, and because there are 4 suits, and once the king is chosen, the remaining 4 cards are from the reduced deck because you have to kick out all the kings, right? So instead of 52 cards, you take 48. So it's 48, choose 4 for the remaining cards. Aces is the same, right? Because there's no difference. What about the intersection, right? So how many hands are there that have 1 king and 1 ace? Okay, not that much harder, right? You have 4 choices for a king, 4 choices for the ace, because 4 suits for king, 4 suits for ace, and the remaining 3 cards, because you have to have exactly 1 king and exactly, or well, in the intersection, you have exactly 1 king and exactly 1 ace. So you kick out all the aces and all the kings. Now your reduced deck has 44 cards, 52 minus 4 times 2 characters, right? And you're choosing 3 cards from this. So this is the multiplicity of the intersection, and the whole answer is therefore this plus that minus the cardinality of the intersection. how many bit strings of length 10 start with a 0 or have exactly 5 ones. Okay, but again, it's not an exclusive OR. So it's okay if a string satisfies both of these properties. All right, so 10-bit strings with exactly 0 is one set. 10-bit strings with 5 ones is another set. And intersection is non-empty because you can start with a 0 and have exactly 5 ones. Okay, so we are going to use the inclusion-exclusion principle, and but each of these sets is easy to count. If you start with a 0 and you have 10 bits, so there's 2 to the 9 choices for the 9 bit. If you have to have exactly 5 ones, so what is it? You're placing 5 ones into 10 positions. You're choosing 5 out of 10 positions where the ones go. So that's the formula, right? And what about the intersection? So the first bit is a 0, and then you're choosing 5 positions out of the remaining 9 to place the ones. Not that harder, right? Not that much harder. And so the answer is the first set plus the second minus the intersection. So what about strings of length 6 over an alphabet, and you have at least 5 consecutive A's? Okay, so strings of length 6, so there is not that many of them, but let's see. So the first string can be like this. You vary the last element, right? The second set perhaps is like this. Yes. The thing is that these two sets have a non-empty intersection. There is a string that is both AAs, the run of A's, what starts the string and ends it. And it's just this. So now each of these have multiplicity 3, right? Because the star element is any of these 3. And the intersection is 1. So the answer is you have 5 strings like this. Okay? I guess you can count this by hand in a sense, right? But you have to watch for the intersections of these sets not empty. So not to double count. Now, what? Okay, what if I have more sets, right? More choices. So the generalization of the inclusion-exclusion principle looks like this. I sum up the cardinalities of these sets. I subtract their pairwise intersections, and then actually I have to bring back the total intersection. Pictorially, it's like this. I'm trying to count cardinality of this union. So it is the cardinality of the blue, the red, and the green, except that I overcounted this region twice because it's part of both the green and the blue. And this one is overcounted twice. This one is overcounted twice. So this region is actually overcounted 3 times because it's part of all 3. So if I subtract out intersections, pairwise intersections, then I subtract out this. Okay, good. I kicked out the 1 double counting of this part. So now I'm down to just counting this part once. And I also kick out this intersection. So I kick out 1 double counting of I. And so with this, but if I remove them like this, then how many times did I remove X? Actually 3 times. It was counted 3 times to begin with in here. But when I removed these, I actually removed each of these again 3 times. So now I'm undercounting this. That's why I have to bring this back. Okay, so it's all like I written on here, but it's just what I told you. Uh, uh, so so for example, let's say you have a drug test on a population, and what you know that, okay, 122 people got one symptom, 88 symptom B, 112 symptom C. But they're not, if you say how many people got at least one symptom, well, you cannot just add these, because perhaps there are people who got both or all three. So you'll be, overcounting them by adding. Well, let's say you know these intersections. So 27 are in the intersection of A and B, 29 in A and C, 32 in B and C. But that also doesn't tell you all information. You also have to know the inner intersection of all three. In other words, how big is this set? Okay, and now you know how to compute, because the total union is the individual cardinalities minus pairwise intersections plus the three-way intersection. Okay, so in fact, these numbers are precisely answers to this question, right? So we can just put them in. Let's say, okay, the different class of problems, but it is an inclusion exclusion problem, or this thing can be solved using inclusion exclusion. You line up 7 people, mother, father, 3 sons, 2 daughters. And how many lines up? And they're all distinguishable. So there's like son 1, son 2, son 3, daughter 1, daughter 2. How many orderings of them are there where the mother is next to at least one of these 3 sons? Okay, so let's count the ways to line up. How many ways to order the family are there where the mother is next to son I, where I is 1, 2, 3. So she's AI is the way of ordering where mother is next to son 1. A2 is all the orderings where the mother is next to son 2, etc. The thing is that these are sets are non-intersect. They're not disjoint. AI and AJ have an intersection. What is intersection? It's all the orderings where the mother is both next to son 1 and son J. Three-way intersection cannot happen, right? I mean, it's an empty set, right? She cannot be next to the 3 or 3 sons. So that's good. Now, how big are these sets? Well, the individual sets is okay. We know how to count them, right? Because these type of problems, how many ways are there ordering 7 elements where element 1 and element 2 have to be next to each other, right? So we conjoin them, and therefore it's like counting 6 how many permutations of 6 elements. But there is 2 ways of conjoining them: mother first, son I second, or son I first, mother second. That's why it's 2 of the 6 factorial, right? Mother SI as a unit and SIM, mother as a unit. So each of them have this. What about cardinality of these? Okay, so again, you take SI mother SJ as a unit, but you can also take SJ mother SI as a unit, right? But either choice you make, now it becomes a way, the way to order 5 different elements. right? The remaining family members and this one sort of hybrid entity. Okay. So there's 5 factorial of ordering these, but there is 2 types. So it's 2 times 5 factorial. And the intersection, the 3-way intersection is 0. And now using inclusion exclusion, the answer is multiplicity of this cardinality of these 3 sets. So it's 2 times 6 factorial 3 times, minus each of these intersections. They all have the same cardinality because it didn't depend on these indices I and j. So I subtract, I get this, and if I order them, then you can see that it is 6 times 6 factorial, and this is 5 factorial times 6. So I can just take the 6 out, and it will be like that. Yeah. And perhaps there is other way to count that makes this very apparent. That why? Because we just arrived as a simplification. But you can ask yourself, like, is there an alternative answer that immediately gives you this? I mean, the answer is only good if it gives you this number, but perhaps you can interpret it differently. And now if you have this alphabet and you have 6 characters and only 4 consecutive A's, so now you have more choices, right? Because set A1, A2, A3, there are like 4 A's with no matter that don't care 5th and 6th element, or don't care first, the 4 A's, don't care 6th, or don't care first and don't care second. And the pairwise intersections look like this, right? For example, these 2 sets intersected mean that 5 elements have to be A, or this and this intersected is like all A's. And the triple intersection, the 3-way, is non-empty, it's just all A's, right? So again, inclusion exclusion, okay, it's easy to count each individual sets, right? This is 6 to the 2nd power, each of these 3 sets, and the cardinality of this is just 6, 1, 6, and 1, right? So the total cardinality is 3 times 6 to the 2 for these 3, minus these, which is 6 plus 1 plus 6, plus the 3-way intersection 1. Okay. Oh, here is a nice. I think this is my last example. So, arithmetic example. How many integers from 1 to 42 are divisible by 2, 3, or 7? Okay, so this is the RSA type of problem, right? Like you had a modulus which is a product of some primes, and for the multiplicative subgroup, you have to kick out all the elements which are not coprime with the modulus. So that will be exactly this. You kick out all the ones that are divisible. There are multiplicities of the factors, okay, of the modulus. So how many of such elements are there? Okay. So let's count all those that are not coprime with 2. In other words, there are multiples of 2. In other words, there's 0 mod 2. Let's count all those that are multiples of 3. In other words, there are 0 mod 3. And let's count all those that are 0 mod 7. Okay. And now, what are the intersections? So these are all, there are multiples of 2, and these are multiples of 3. The intersections has to be multiples of 6. They must be 0 mod 6. The intersection here is that they are multiples of both 2 and 7, meaning multiples of 14. And the intersection here is that they are multiples of 21. And then there is a three-way intersection, right? There are multiple of 42. And now what are the cardinalities of these sets? Well, they're not hard. So, so by inclusion and exclusion, if we could count all these cardinalities, then we would know the answer to our problem, right? We would take cardinality of these first three, subtract cardinalities of the pairwise intersections, and add the cardinality of the three-way intersection. And we can count each of them, right? Because the set from 1 to 42 that are divisible by 2 is just every second, right? Is 0 mod 2. So it's the total number divided by 2. Likewise here, how many are 0 mod 3? Well, every third. How many are 0 mod 7? Every seventh, right? And it's the same answer to all these questions, because 42 is divisible by each of these, right? So it's going to be even this method of counting. There's not going to be like some floor or ceiling anywhere, right? So all of these are thankfully divisors of 42. So each of these has an integer answer, right? 21, 14, 42 by 7, 6, etc. Right? So I get the answer, right? The reason why phi in RSA was p minus 1 times q minus 1 is related to this. It comes exactly from inclusion and exclusion. It is because when you kick out the RSA modulus over p, which is q, then RSA modulus over q, which is p, and then you have to bring back the one element that you double counted. So n divided by n, which is 1, right? So that's why phi is p times q, the total, minus p minus q minus 1 plus 1. Okay, and if you generalize it to 4 sets, you would have the same property. You take first layer cardinalities, then you subtract pairwise intersections, then you add three-way intersections, then you have to subtract the four-way, etc. And you know, we have some examples. In general, if you have n sets, then the same formula generalizes, right? Like you take the first layer cardinalities, you subtract pairwise intersections, you add three-way, you subtract four-way, you add five-way, you subtract six-way, and so on. You go. Okay, which of course you won't have examples like this, but that's how you would do it in general, right? And I have some example here that you can scrutinize on your own because I'm over time. Okay. So I will stop recording.